Okay, today I'm going to talk about the Mobius inversion problem, or the Mobius inversion formula. We've got a whole bunch of useful machinery here, and I'm going to bring it all together to this rather amazing formula here. So basically, what we've got is f of n. Actually, let's start at the beginning. F of n is multiplicative. So what that means is that f of no, it doesn't. It means that n and m co-prime implies f of mn equals f of m f of n. We've also got capital of f of n equals the sum d divides n of little f of d. So there's the relationship between the uppercase f here and the lowercase f here. What I'm going to do is I want to invert this. I'm going to invert this by saying f of d equals something times f of n. In fact, f of n here, in fact, equals something of f of n. We want to invert this. We want to invert this process here. And it's quite astonishing that you can do this. Let me just give you the formula and then we'll see what happens. F of n equals sigma over d divides n, mu of d, let me just write it out, capital F of n over d, where mu of d equals the Mobius function that we covered in one of the screencasts before. So, well, we've got what we said we were going to do. We've inverted. If we know capital F, then we can figure out what the little f was, where capital F and lowercase f have got the relationship built in here. So we can turn that formula inside out. So the Mobius function is instrumental in this. Oops, what happened there? Oh, it's here. Don't know why that happens. Okay, so how am I going to prove it? I'm going to give a very sort of quick proof of it. Oh, I just want to say something else. This is also equal to sigma over d divides n of mu of n over d times f of d. So we can choose which way. You just think about that and it's pretty obvious, because all we've done is as d runs over divisors, then we're basically writing d dash equals n, and we're using d dash instead of d as a summation variable. So that's two ways of inverting f of n here. Sometimes you need one, sometimes you need them both. How do we prove this? Well, we need a whole bunch of, well, I'll just remind you of one feature of the Mobius function, that sigma over d divides n of mu of d equals 1 if n equals 1 and 0 if n is greater than 1. So if I saw f of n equals this, then this function here has got this very nice simple straight property that it just detects whether its argument is 1 or not. So this is a very nice sort of neutral, simple function, simple feature or simple property of the Mobius function that we can use. We can use it to our advantage. Okay, well let's just start with this thing. So I'm going to. Oops, Daisy, how did that happen? Not sure where we are now. Oh, here we go. Well, let's just write out the right hand side, which is sigma. So the right hand side equals sigma over d divides n, mu of d, where mu is the Mobius inversion function, capital F of n over d. And I'm just going to write out what that is by definition. Sigma over d divides n, mu of d times this thing in brackets, which is f of n over d. So I'm just going to write that out as sigma c divides n over d of little f of c. That's just by definition of f of n, except that we've got a c here. Which slightly changed our notation. So this thing here is equal to that. Okay. So what I'm going to do now is observe that this summation here can can commute with mu of d, so it's sigma, let's try that again, sigma d divides n, sigma c divides n over d, mu of d, f of c. There we go, like that. And then I'm going to make use of a nice feature, which again I'm not going to prove, which is that if d, oops, a daisy, if d divides n and c divides n over d, then this implies and is implied by if and only if, I guess, c divides n and d divides n over c. Okay, there's a nice little intermediate result that we're going to use to process this formula here. So what does this equal? This equals sigma over c divides n, sigma d divides n over c, f of c, mu of d. All I've done is taken these two summations, d and c, and I've used this little result here, which is so well, it's straightforward, that. Okay, well, let's have a look at that. That's equal to sigma over c divides n of f of c, sigma d divides n over c, mu of d. Again, I'm using the fact that I can take this, function f of c, and that commutes past this sigma operation here. Equals, what does that equal? That's sigma over c divides n, f of c, times sigma d divides n over c of mu of d. And this thing here, that equals 1. Remember that we've got this formula, sigma over d divides n of mu of d equals 1 or 0. 1 for n equals 1 and 0 for n greater than 1. Okay? There's no special name for that function, but there it is. So this equals 1 if n over c equals 1, i.e. n equals c. So it's only if n equals c that this function has got any is 1. And if n is not equal to c, if this ratio here is not equal to 1, n over c is not equal to 1, this whole summation drops out and it's 0. So we've got sigma over c equals n, because that's the only contribution that we've got from this bit here. F of c equals f of n. Well, there we are. There we have it. How anybody discovered this formula, I've got no idea. It's quite nice. I'm going to write that out again. I'm going to write this whole thing out again. If f of n is multiplicative, and f of n equals sigma over d divides n f of d, then little f of n equals the sum over d divides n of mu of d, capital F of n over d. There it is. Now again, I find this quite surprising. I mean, it's one thing to state it, it's quite another thing to think about it. If we look at this relationship here, I would expect that capital F of n will be somehow sort of flatter than little f, because this process of summing over the divisors of n, I would expect to flatten out or make somehow smooth out lowercase f, so equals f of n. So I would expect this to be smooth in some sense. And I'd expect this function little f of d to have all its lumps and bumps smeared out somehow by this peculiar average weighting process. So it's a matter of some surprise to me, even now when I think about this, that you can actually invert this formula. And we can do it like this, and this is called the Mobius inversion formula. And there it is, and I'm going to stop right there.